In this video, I'll look in more detail at how ADHD medications work. Now, this is perhaps one of the more complex videos in this section about treatment, and to help me explain better, I'm going to be using some diagrams. I'll focus on the four main ADHD medications: methylphenidate, the amphetamines, including lisdexamfetamine, atomoxetine, and then guanfacine and clonidine. Before going into the specifics for each medication, it's helpful to think about where these medications are working. We've discussed in a previous video that there are several important brain circuits implicated in ADHD. These include the executive control networks, the reward networks, the corticocerebellar timing networks, and the alerting network. Much of the general neurotransmission across these networks is mediated through the excitatory neurotransmitter glutamate and the inhibitory neurotransmitter GABA. However, the activity in these glutamatergic and GABAergic circuits is heavily modulated by the effects of both dopamine and noradrenaline. All the ADHD medications we're considering have an effect on noradrenaline, and the stimulants and atomoxetine also have important effects on dopamine, particularly in the prefrontal cortex, which we know is central to several of these circuits that are implicated in ADHD. Now, both over and underactivity of dopamine and noradrenaline results in inefficient neurotransmission through these circuits and has been associated with poor performance on a range of cognitive tasks that are also known to be implicated in ADHD, the so-called inverted U curve. For ADHD, the theory is that too little dopamine and too little noradrenaline are available, and it's hypothesized that the ADHD medications reverse this deficit by increasing dopaminergic and noradrenergic neurotransmission. While the end effects of optimizing dopamine and noradrenaline on neurotransmission in these circuits are similar, they actually achieve these effects through opposite neurochemical mechanisms. Dopamine is responsible for modulating the signal that is passed on through the postsynaptic neurons. Optimal levels of dopamine optimize the signal, whereas noradrenaline is responsible for reducing the amount of noise in the system, with optimal levels of noradrenaline reducing noise to a minimum. The ADHD medications are actually working at the dendritic spines on the dendrites of cortical neurons, where they modulate the information that's fed in from presynaptic neurons and therefore modulate whether or not a signal is passed on to the next neuron. For much of the rest of the talk, we're actually going to focus on the region circled in red towards the center of this diagram. So as hinted at already, when we blow up this area and look in detail, we see that the actions of dopamine and noradrenaline at the postsynaptic neuron are opposite and complementary to each other. Dopamine, which is shown on the top right-hand side of the diagram, activates cyclic AMP, and by doing so leads to an opening up of the so-called HCN channels. Opening these channels acts a bit like pulling the plug out from a sink, a basin. and reduces the amount of noise that's entering the postsynaptic neuron. Whereas noradrenaline, shown on the top left, reduces cyclic AMP, closes the HCN channel, and through that puts the plug in and increases the amount of signal and the likelihood that an impulse is going to be sent down the axon. As I mentioned earlier, it's through their actions on dopamine and noradrenaline that the various ADHD medications go on to influence the neurotransmission in the various circuits involved in ADHD. Let's start with talking about methylphenidate. It is shown as the teal diamonds in the diagram. If you look top right, you will see that methylphenidate binds to the presynaptic dopamine transporter. This blocks its action, which is to take dopamine back up into the presynaptic neuron. Through this blocking of the transporter, there's an increase of dopamine in the extraneuronal space, increased stimulation of the dopamine 1 receptors postsynaptically. This opens the HCN channel, reduces the amount of noise entering the system. Importantly, if you now focus on the top left of the diagram, you'll see that methylphenidate, remember that's the teal diamonds, also binds to the noradrenaline transporter. This means that it blocks the reuptake of noradrenaline and increases the amount of noradrenaline, closing the channel, increasing the signal from the incoming neurons. Now, actually, there's a further twist to this story, as there are very few dopamine transporters in some regions of the brain, including the prefrontal cortex. This means that most of the dopamine in these regions is actually taken back up by the noradrenaline transporter. So in summary, by blocking the transporters, methylphenidate increases the levels of both dopamine and noradrenaline, which in turn increases the signal and reduces the noise and increases the efficiency of neurotransmission across a wide range of key neuronal circuits. Let's move to the amphetamines. They're shown as the green pentagons, and actually the amphetamines also do all of the same actions that methylphenidate does. However, they have an additional trick up their sleeves. The amphetamines are smaller molecules and so are taken up into the presynaptic dopamine neuron by the dopamine transporter, as highlighted at the top right of the diagram. But notice that they're not taken up into the noradrenergic terminals. Once inside the dopaminergic neuron, they directly stimulate the release of dopamine into the extraneuronal space, and this further increases the dopamine available and reduces the noise. These differences do not necessarily make the amphetamines better than methylphenidate, but they do emphasize that despite the similarities, they are different drugs, and they're different in several key ways that can help us to understand why some people respond differently to one and the other. So, that is the stimulants. I said at the top of this video that this is quite a dense and intense section. So what we've decided is to split the video into two parts. I'm going to move on in the next video to talk about the non-stimulants and their mechanism of action. I strongly suggest that you watch that second video quite soon so that you've still got in mind all that you've learnt from this one.